Galina Churkina is a professor of urban ecology at the Technical University of Berlin. Her research focuses on the feedback loops between urbanization and climate, directed at the resulting societal consequences. Her previous research positions include a visiting fellowship at the Yale School of Forestry and Environmental Studies, where she was the lead researcher on buildings as global carbon sinks. She has also worked at the Potsdam Institute for Climate Impact Research, the Institute for Advanced Sustainability Studies, the Max Planck Institute for Biogeochemistry, and the School of Natural Resources and Environment at the University of Michigan. In her contribution, Galina explains the connection between the building demands that will arise globally due to urbanization and population growth and the transformation potential of urban timber construction.
I'm going to talk about building a global carbon sink or carbon sequestration in cities. I will explain what options for storing carbon exist and why transition to urban wooden construction could be powerful in balancing the global carbon cycle and mitigating climate change. Carbon sequestration is removal of carbon from the atmosphere and its subsequent long-term storage on land and in the oceans. Probably the largest amount of carbon in the Earth's history was sequestered 350 million years ago. This carbon was sequestered by giant fern-like woody plants, which grew fast in warm and moist climate, but also easily fell and toppled. Over time, they created a thick mat of dead plants, which was buried as it is and turned into deposits of fossil fuels. In the 19th century, urban and industrial growth prompted by the Industrial Revolution have gradually depleted land-based carbon pool and increased atmospheric CO2 concentrations. High-reaching and heavy load-bearing urban building construction from concrete and steel are produced with raw materials and fuels extracted from ever deeper layers of the Earth's crust were intensive in both energy consumption and greenhouse gas emissions. At present, about 11 gigatons of carbon is emitted annually from burning fossil fuels and land use change, such as deforestation. So where does all this carbon end up? Currently, only half of the carbon emitted from burning fossil fuels and land use change remains in the atmosphere. The other half is absorbed by land ecosystems and the ocean. Land ecosystems, and especially forests, acted as a strong carbon sink for almost a century, but they may sequester less in the future because of increasing frequency of fires, insect outbreaks, prolonged droughts caused by changing climate. The question, where else can we sequester more carbon? Cities is the fastest expanding ecosystem worldwide. Urban population is projected to increase in the next 30 years. New urbanites will need new infrastructures to be built. Can we use this trend to create a new pool of carbon? The currently most used construction materials, such as steel and cement, cause direct and indirect carbon emissions. These emissions cannot be reduced to zero, even if only renewable energy sources are used, because of chemical reactions involved in the production of both steel and cement. Contemporary construction across the world has two additional poorly researched yet relevant impacts on the carbon cycle. First, the production of cement, concrete, asphalt, and other materials require vast amounts of sand extracted from beaches, rivers, and seafloors. Second, mining can lead to extensive local deforestation. The sand mining not only exerts substantial pressure on the available deposits, which have been an increasingly scarce global resource, but also compromises the carbon uptake capacity of the aquatic ecosystems disturbed during extraction. Together, the mining infrastructures and the development of mineral commodity supply chains are responsible for disproportionate loss of forest surrounding mines and resulting loss of stored carbon. Mining-induced deforestation in Brazil alone was responsible for 9% of all Amazon forest loss in 2005 until 2015, 12 times more than their area deforested within permitted mining leases. Therefore, the demand by the contemporary global building sector for construction materials will remain a major source of greenhouse gases unless appropriately addressed. Buildings which are designed to stay for decades are an overlooked opportunity for long-term storage of carbon because the most widely used construction materials, such as steel and concrete, hardly store any carbon. The above-ground carbon density of a city increases with rising housing density and building height of buildings which are designed with timber, if they're designed with timber. Carbon density of timber building can surpass that of soil and trees in a mid-rise city, although soil and trees store more carbon than buildings in suburban developments. A 5-story residential building structured in laminated timber can store up to 186 kilograms of carbon per square meter of ground area in the primary structure. That is more than in the above ground biomass of the natural forest, with the highest carbon density typical for the coastal range ecoregion of North America. We estimated that what implication transition to timber construction from steel and concrete in the next 30 years could have for carbon emissions and storage in new buildings, which would accommodate 2.3 billion new urban residents. We considered several scenarios accommodating different rates of mass timber adoption in construction. In a scenario when 50% of new buildings are constructed with timber, the carbon storage can be up to 11 gigatons of carbon, and total emissions from construction would be reduced by 5 gigatons of carbon. The cumulative emissions from manufacturing mass timber materials are lower than those from mineral-based materials, not only because of relatively low embodied emissions of mass timber, but also because of the lower material intensity of wood compared to mineral-based materials. Low material intensity reduces the material stock per floor area or capita, an important contributing factor to the embodied emissions of materials that has implications for the energy demand of materials. The most drastic shift to timber buildings with 90% in the 90% timber scenario will yield the highest carbon amount stored in buildings and the most savings of carbon emissions. In this case, emissions from mass timber production exceeded the emissions from mineral-based materials and account for 80% of the cumulative emissions from material manufacturing. The added processing steps and the introduction of chemical adhesives in the lamination process combined to increase the embodied energy of mass timber and associated emissions of CO2 as compared to those of solid wood. while scaling up the mass timber industry, CO2 emissions from mass timber manufacturing and related forestry operation will ultimately have to be reduced. A recent study demonstrated that these emissions can be disproportionately high in regions with active forestry operations. The net emissions from the forest sector amounted to 50% of emissions from the energy sector in Oregon, in the United States. A reduction can be achieved by improved forest harvests and product manufacturing efficiency, longer forest rotations, using renewable energy sources, using lignin-based adhesive technologies, or mechanical lamination techniques. Let us return to the overview figure and complete the big picture. Cities built from bio-based materials, such as engineered timber and bamboo, can serve as constructed carbon sinks. Storing and maintaining carbon in these densely constructed carbon pools will help replenish the terrestrial carbon storage, thereby reducing current atmospheric CO2 levels and offsetting future emissions. Construction with bio-based material will create a global carbon sink and help mitigating climate change under two conditions, which are: the first, the harvested forests are managed sustainably, because we want to protect the forest which not only sequester carbon in significant amounts, but also harbor much of the world terrestrial biodiversity, providing habitat for various animals, birds, and insects. Forests are also a source of subsistence living in some cultures, where hunting and food gathering in forests contribute significantly to people's diets and lifestyles. Moreover, forests are an important moderator of the Earth's climate, and this function of the forest is not limited to its ability to balance the carbon cycle. Second, the carbon pools in timber cities have to be maintained and gradually enhanced along with forest carbon pools to ensure a long-term lock-in of carbon on land, which can be achieved through more durable construction detailing that provides longer timber building lifespans, stimulating markets for used wood materials and for technologies that convert used wood into other long-living products, along with sustainable management.